Hello, and welcome to another exciting episode of Spin the Rotor. And if people are joining for the first time, I'll just mention here what's going on is that this is a pulse motor, and there's a sensor there that detects when a magnet comes by, goes through to here. Use this battery, and then you put a coil by the magnet, and you pulse the coil, and the thing spins round and round. And then when the coil is pulsing, then there's an inductive spike, and you stick it in this cap, and then you see what the voltage is on the cap. Now that voltage oftentimes doesn't change too much depending on what you're doing. It's like 80 volts or something. So I put just a big resistor. I think this is 100k ohm. And that brings it down to like 40 volts, and then you can also see that voltage changes a lot more. It seems there's oftentimes just a peak voltage, but how much power is going into the cap changes, and you can see that once you have like a 10k ohm resistor there. So that's what that's doing there. Now for people who've been following along, I'll just give an update on what's been going on. So as I was mentioning, I wanted to reprint this rotor, and for a couple of reasons. The first is that when this was part of a two-part rotor, I had this extra part here. I won't go into why I did that, but it made it harder to get it to spin really cleanly, and so I wanted to get rid of that. And then I also had a little bit of difficulty that I didn't like how the bearing was set. So it took a couple tries. I mean, there's some tries where, it's like, oh, the first layer's not going down. But there was one where I printed the whole thing. It took 10 hours, and then there was like a line in the middle where it wasn't getting much, it would have just broken apart. But the second try worked, and ain't she pretty? I think that looks great. So the bad thing is I'm probably not even going to use it much, but I haven't even spun it yet. But it looks like my idea here for how to mount the bearing is working. And what I've done is the width of this hole is equal to, obviously, the width of the bearing. And then when it gets to the bottom, when you put the first layer down, there's just a tiny little bit of overlap. And so it bumps into that, and that's where you know that it's snug and flush. So I think this thing's going to spin great. But as I was working on this over a few days, I got rid of like 80% of the wobble on this. I mean, it now looks pretty good. It's still got a little bit of wobble. But that's where things are now, and I'm not sure how much of this I'm going to use. I've been doing really a good deal of experimenting. And what we've seen recently was that when you had a coil like this, and the coil was fairly far out, it spun fine. You bring it in, the amp draw goes down, and then as you continue to bring it in, the amp draw continues to go down, but the rotor starts to slow down, which is strange. I mean, the only way that makes sense to me is if there's a feedback. It's the magnet hitting the rotor is actually feeding back to source there. But the spike also, when I say spike, I'm talking about the power going into here, goes down. And also when you put a pickup coil there and run it out to another cap here, you can see that even the torque goes down. So you start bringing this in closer and closer, and eventually it's a less powerful motor. And you're also getting a worse spike, although the amp draw is going down. But the decrease in the amp draw doesn't compensate for the decrease here, I would say. I mean, I don't know. I mean, I have to look at that more and think about it more. So let's just get an idea of how complicated and fun this game is. So, I mean, the game, of course, is just gradually, incrementally improve the motor. And the key kind of issue here is how do you productively put wire next to a permanent magnet? so that you're not getting things like the rotor slowing down. And one of the things we've been looking at is what axis is that? That's the y-axis, I think. We've been looking at the y-axis, but you have to realize this is, it's all in 3D. So you have the pulse, the trigger there, and so, there's also the x and the z axis. And so that's the first thing, is working to get a handle on the y-axis, the air gap. Then also, where is it? Where do you want it on the x-axis? Where do you want it on the z-axis? And that's a little bit, I think, more straightforward within the plane of a particular, point on the y-axis. You just kind of move it around there and see what's going on with your amp draw with this and what you're getting out there. But then there's also the coil shape, and one hypothesis has been that this is about twice the width of the magnet, and maybe when you're bringing it in close there, this stuff that's not directly over the magnet is going down and seeing the opposite side of your permanent magnet, which is counterproductive. And I think that's what's going on. So first, one of the things I did was I wound a couple coils like this, and they do behave a bit differently in that effect is a little bit mitigated. But then I also got to thinking about it, is that you don't really know if it's the overhang or this electromagnet is 2 inches long and your permanent magnet is a 1/2 inch. So in other words, if you had, your electromagnet 5 inches, you kind of expect the magnetic field to be going way out like that, where if it was very flat, and this at least is what I would think, the field would be more flat as well. So maybe it doesn't necessarily have to be the overhang. It could be that the thing is too high. So, what I ended up making, where is one? I ended up winding 3 coils like this. This is actually, it's sort of like a little bit of an optical illusion, because these are 1 inch by 1 inch by 1 inch, but because they're circular here, the diameter is 1 inch, but it's 1 inch to here, and it's 1 inch across there. It looks taller than that, but they're essentially 1 inch. There's a tiny bit. There's an 1/8 inch here, and an 1/8 inch, or a 1/16, something like that. But they're basically 1 inch by 1 inch by 1 inch. And so that's what I've been working with. Get out of my way. And it's sort of like, well, let's just see what these do. Because, I'm not going to go any smaller than that, because, pretty soon you're going to have like a little thumbnail coil. So, I think this is, this is small enough. And I can confidently say at this point that I don't know what's going on. It's interesting, and I'm starting to wonder, maybe if you put a magnetic flux path between the two magnets that are 180 degrees opposite, it would be different. So there's good and there's bad. Well, lastly, even before I get to that, just in terms of this being, just complicated, is so you have all of this in 3D, but then also you can rotate this. So this is, I believe it would be called axial flux, but you can run it like that, and that would be one way of doing it with radial flux. You could run it and it runs like this. It doesn't run as well this way. It runs well this way, and it runs well tangentially. So that's yet another way to set this up with what's called a radial flux. Those would be analogous for people who have followed along some of the Bedini stuff. Those would be analogous to the window motor and the zero force motor. I think this would be closer to the, well, it's confusing because this magnet is not oriented this way, but one of them's analogous to the window motor, and one of them's analogous to the zero force. And I will say that the best thing I got, both for spike it was only marginally better, both for the spike and even for torque at a particular air gap, was a radial flux version, like this. But you don't want to, you don't want to generalize too much, because maybe, a little bit different coil shape or something. But one generalization I think that's safe is that the radial flux can be good. So I said there's good news and there's bad news. The good news: when you have a sufficient air gap, you can keep adding wire, and three things happen. So the first thing that happens, let's say you add a second coil, 180 degrees opposite. The amp draw goes way down. It almost cuts in half. It doesn't cut in half. I don't know why, because you just doubled the resistance, but it has to do with the impedance of the two coils versus the one. But you almost cut the amp draw in half. In general, the rotor speeds up as compared to one. Not a lot, but it's just that now you're not hitting it where it's making the rotor want to do that. You're hitting it 180 degrees opposite, which is better. So you get, maybe 5% extra rotational speed. The torque also is the same. You're using less amp draw. Now, the spike goes down, but the spike doesn't go down as much as your nearly 1/2, loss of amp input. So, in other words, you lose a little bit on the spike, but you lose a lot on how much you need to power this thing for it to run at the same speed and with the same torque. And that actually brings even another variable in, which we haven't talked about, I've looked at briefly, is pulse width modulation. With this setup, and I think part of it is that I've got these big 1H magnets, you get improvement. I mean, it slows down a bit with a briefer pulse, and you lose some torque, but the spike compared to the input energy, there's a modest improvement, but it's not nearly as dramatic an effect as if the coil's there versus there. So I'm not worrying too much about pulse width modulation right now, but that's another thing to optimize. Now, so we got one good news, and then I'll talk about two bad news, and then we can talk about the good news again. When you start bringing even this small coil in this close with it's not a tiny air gap. It's, still like a 1/4 inch. But what happens is okay, let me be clear on this. When you bring it in with a single coil, this is why I'm saying it's like, what in the heck? When you bring it in with a single coil, it continues to improve with this form. Okay, so your spike is going up, you're losing less amp draw, and your rotor is speeding up until you get in like really close. You can put this thing like under there, and it's just, like a very small air gap. But here's where it got weird. Now, when you're in close and you add a second coil, now the rotor slows down. You still get the decreased amp draw, but the rotor slows down. The spike just plummets towards the ground. And when you add a third coil, it gets even worse with the spike, and it slows down more, and it's lower torque. Okay, so we got this sort of medium air gap going, and okay, it's off. Not real high torque, but it's spinning, and it's going to spin up. We got, all right, I like it. We got this hooked up to here, kind of showing the power going out here. Now, the other thing with this air gap, what we'll see is as it spins faster, the power coming out, the power coming out from the spike improves. When you get it with the narrower air gap, the faster you go, the power from the spike decreases. So that's another bad thing with that very narrow air gap. See how the spike's going up there. Let me put in an amp meter. So now we have it spinning up, and we have the amp meter there. You know, oops, I just knocked it off. But we're drawing, I don't know, oh, come on. I'll fix that later. We're drawing, you know, I don't know, like 45 milliamps. And then as it speeds up, that'll maybe, you know, it won't be dramatic, but it'll drop to maybe like 40, maybe even 35 or something like that. Probably like 40. And that's because of the reactance of the coil. It's not a huge difference. You know, if there's like 100 RPM or a 10% change in rotational speed, you're only going to see a milliamp or two difference. But it is there. And we can see the output across the resistor for the spike is continuing to climb as this thing speeds up. So we'll let it get up to speed, and then we'll put in a second. And as I said, I think with this air gap, you're in a position where everything's improving. And then when we go further down, you get in a position where most things are going the wrong direction. And then if we wanted to, you know, put this in as a pickup coil and then put a meter on here, there's a little diode, you know, so you rectify that and then put a resistor, like a 100 ohm resistor across there. And so that gives you a consistent load. And so what you can see is, you know, maybe two iterations both spin up to 1,000 RPMs, but when you load it, if one drops to 800 and one drops to 500, you know, well, the one that drops to 800 has a lot more torque. In general, of course, the faster it's going, the more torque. But you do see that because, again, these things can step on their toes and whatnot, and so on and so forth. Let's let this spin up and get the RPMs, and we'll put in a second one. Maybe even put in a third. Okay, so if we look at RPMs, seems to be holding steady there, about 543. It just fries my bacon that I lost 2 pages of this data, but let's just, here was my first go at it, so we'll do it a fourth time. And you want to fiddle around on the X and Z axes. That's important to, you know, because the first time I was doing that, the RPMs were like 314. Now we're at 543. Let me grab the thing here. So 543. The amp draw. What is the amp draw? I'd say it's 40, maybe 41. Can we get away with 40 or 41? Before we were at 39. Call it 40. Let's call it 41. Spike is at 28. 28. So we know we have a 100k ohm resistor. So when you when you do all the math there, we're getting 4.7% back out of the spike. But that's better than the 4.1% there. So this is where that is, 4.7% back on the spike. I'm not even going to bother. Should I do that? It'll take too long. This is going on forever. But you put this under there, measure what you're getting out here. The RPMs are going to slow down, see what your spike is, and so on and so forth, and see what you're getting out from there. So you'll add another, you know, maybe another 4 or 5% or something doing that. Now let's add the second coil and see if we're productively adding wire. Okay, so we've added a second coil, and the rotor's speeding up, so we know that we don't have the coil upside down. So let's let this spin up. As it's spinning up, I should have shown this sooner, but what you see is that, again, as it's speeding up, the spike is improving. So yay. But we also see it doesn't look like the spike's going to make it back to the 28 volts it was at before, even once it's fully spun up. But the spike's moving in the right direction, so you're going to like that. So this is spun up to about someplace steady, about 560 RPMs, as opposed to 543. So it's faster. And it's drawing, it doesn't want to focus. I think, let me get a magnifying glass and look at it. When I looked at it, I think it's 24 milliamps. And this was, it's between 22.1 and 22.2 for that voltage. So it's gone from 28 down to 22, but the amp draw has gone down, so the spike is actually a tiny bit better. It's now 5% of your input power is coming out as output power to that spike. And the other interesting thing is that you're drawing almost half the amperage and you're spinning faster. And if you load it, you see that it also has, you know, like equivalent torque. It's actually a little bit better on the torque. So in other words, this one might slow down like 25%. This one will slow down 20% with the same 100 ohm resistor, the same coil there. And so since this is now 97 milliwatts instead of 166, what you're getting out there is a bit better. It's still only, you know, like 5 or 10% or something like that, but it's a little bit better. So that in and of itself is just strange, because we could add a third coil. I've done that. You add a third coil and you get the same pattern. This spike voltage continues to go down, but it improves as the rotor speeds up. You don't really get any further improvement. It'll be like 560 again, and I think that's because, you know, the rotor is a tiny bit imbalanced now. I haven't tried it with 4 yet, but the trends are the same, and now it's, you know, there's another third knocked off of the amp draw, and you're going the same RPMs and the same torque. So that in and of itself, if we just forget entirely about the inductive spike, that's kind of interesting, because, you know, what if the rotor was the size of this table and you had, you know, 150 of these coils going around there? So that's interesting. Can you just indefinitely continue productively putting wire there? And with this air gap, it looks like you can. You're just starting from a place where, you know, what you're getting back is minuscule. And I'll just be conspiratorial here for a minute. Is like, does this apply to electric motors that aren't pulse motors? That, you know, basically the bigger they are, the more magnets, the more wire, the more efficient they are. One of the things I find curious, like with the Tesla, they're planning the Tesla, you know, what do you call them? You know, long haul truck. And from what I understand, they're using the same motors as they use in the Tesla 3. So it's sort of, well, I think you could make the motor like twice as big. And if these trends apply to something that isn't a pulse motor, is there a reason why, you know, they're not going any larger with the motors? I don't know, you know. And it's interesting. I mean, I saw a teardown of one of their motors. I won't go into that. We'll talk about that another time. Let's drop this down to the narrow air gap, and I'll show you how everything goes kerflooey. And as I said, because I know that the bipolar is more efficient, I just want to go straight to the bipolar rather than spending too much more time on this, and see if the behavior is the exact same. Like, is there an optimal air gap? There's again going to be a sweet spot on the X and the Z axis, but how does the air gap behave with the bipolar? But let's drop this and I'll show you what the problem is. So I've just gotten rid of these little tape spacers. Now we'll put the shelf back on and do the same thing. So initially here with one coil, everything looks copacetic. So, but it's it's the two coils. When you try to add more wire, this won't focus. But I was seeing it's like 30 or 31, or rather, what is it? It's 35 milliamps. So no, it isn't. It is 30 milliamps. So we've gone from 41 to 30 milliamps, but the spike has dropped from 28 to 25. So let's put that in. Okay, so when we put those numbers in, we've gone from 41 to 30, 28 to 25. You're now getting 5.1% back instead of 4.7. So that's great. And if we look at the rotational speed, it's now 805 as opposed to 543. Now where everything goes sideways is with the second coil. But that's neat with the single coil. I mean, you've gone up to 805 and your amp draw has gone down. But let's add the second coil. Here, I'll also just show this to you as it spins up. Now, I might need to optimize where that's going. But you can see the spike's gone to heck. And then the worst part of it is as it spins up, the spike is no longer getting larger. The spike power output is going the other way. And that's the exact opposite of what we want and what we saw with the larger air gap. Okay, so the one good thing is the amp draw has gone down. It's like the amp draw is now down from 24 to 12. The spike is at 12.6, 12.5, and you recall when it was going slower, it was like 14 something. So the spike's moving the wrong direction, and if we plug that in, we're now getting 3.2% as opposed to 5% back. So that's moving in the wrong direction. The RPMs are 626 as opposed to 805 with the single coil. That's moving in the wrong direction. And if you load it, which it's not loaded now, it also has less torque. So that is a head scratcher, isn't it? Once this coil was sized correctly, or, sized differently, maybe it's correct, you did improve things all the way down to, with the larger coil, the single coil was doing worse there. When you add a second coil, it's getting worse. Now, I don't know why. Maybe it's not solely the size of the coil. Maybe I don't know why. Okay, I just don't know. But it's also, isn't it incredible? Just that change in the air gap gave this tremendous change in behavior. Where a little bit larger air gap, it's less efficient, but you keep adding wire, and I've added 3 coils, and it keeps getting better. Here, got worse. I added a third coil. It got even worse. Both the spike and the rotational speed and the torque. So I don't know. As I said, it's a head scratcher. It would be worth cutting this in half and seeing, you could probably find a spot where maybe you're between that 543 and the 805, between 41 and 30 milliamp, but you could still add wire productively. However, it occurred to me that I've noticed that the bipolar commutation is more efficient. And so I have no idea how it's going to behave with bipolar commutation, but that's probably what you want to go with. So rather than, beating my head against the wall over this, or, just running with it with bigger air gap, but rather than do that, I want to find out how it's going to work with bipolar commutation. And if I'm going to do bipolar commutation, you probably don't want, you don't want the 4 magnets. Let me shut this down. And that's because they're so far apart. So that is to say that, you know, if you're, say at like 22 degrees here, you're pushing off one, and if you're doing it bipolar, then you're pulling on the next one, but the next one's so far away that it's only a small improvement between monopole and bipolar commutation with 4 magnets like this. When you have 6 magnets, it's a bit more dramatic of a difference, because now there's only 60 degrees between each one, and it can really start to get a bit of the push-pull going on. So might as well print a 6-magnet rotor and run it bipolar, since I want to look at bipolar commutation, and then see, does this happen the same when it's running bipolar, or maybe it does something completely different. I mean, I have no idea. So what I need to do now is print a six pole rotor, and hopefully that will go a little bit smoother, and I'll get it on the, you know, within a day or two. The other thing that I'll do while I'm printing that is I also want to look at 22 gauge. This is 26 gauge wire that I was using before. Look at 22 gauge wire, and I have a strong suspicion, for reasons that I won't go into here, but that the power coming out into here will be a greater percentage than 4 or 5%. Might not be much better, might only be like 5 or 6%, but it will be moving in the right direction. So I'll wind some 22 gauge coils with this coil form, and if I'm running into problems getting the 6-pole printed, I'll at least look at that with 4-pole, and then we'll get the 6-pole printed, maybe look at it briefly as a monopole, and then run it bipolar and see, look at the air gap. That's the main thing. That's my main question right now, is does the air gap behave the same with bipolar commutation as with monopolar commutation? And you know, you could think of goofy stuff. I mean, you could think, I'm thinking about, I don't think it would make a difference with it monopole, but maybe with bipolar. I mean, if you had a magnetic connection path, magnetic flux path, basically put a welding rod between here and here, would that change that behavior with when the air gap gets real small? I hope people are having fun. I'm certainly enjoying this, and thank you for your time and attention. And next up, 6 poles and bipolar commutation, and we'll put it all in the spreadsheet. And the goal here through the spring is just keep improving it. Just keep making incremental improvements, and then you have an idea if you really want to try and take it up to 24 volts or something like that, how you want things set up. So again, thanks, and stay healthy, everyone. Talk to you later. Bye-bye.